Hello everyone, my name is Christos Kirkou and I'm a research lecturer at the GEOS Research and Innovation Center of Excellence at the University of Cyprus. Today I'm excited to present our work on a lightweight and efficient convolutional neural network for crowd counting. Our work focuses on optimizing neural network performance for real-time crowd analysis, especially targeting aerial imagery. This is the outline of my talk. I will first go over why do we need to work on improving crowd counting, then provide some relevant research in this area and the potential for improvements. I will then present the main methodology of our work, the experimentation and datasets we used, and some results. Finally, I will provide the conclusions of our work and future directions. A real-time system for counting and locating people using camera inputs can revolutionize crowd surveillance, particularly through aerial imagery, which offers an expansive field of view. This technology can be useful in scenarios like parades, concerts, outdoor sporting events, riots, and malls, where crowd sizes can range from hundreds to thousands. Estimation in such dynamic settings is challenging and prone to inaccuracies. An automated system enhances situational awareness and decision-making by providing precise, automated crowd analysis, ensuring safety, efficient resource allocation, and event management. Our paper addresses the critical challenge of balancing computational efficiency and accuracy to enable real-time processing for crowd counting and localization, particularly when utilizing drones. By optimizing algorithms for aerial data, our approach effectively bridges the gap between prediction speed and prediction accuracy. Our research enables crowd counting and localization in real time on high-resolution images, which is crucial when dealing with small objects. This makes it highly suitable for high-stakes scenarios where rapid and precise crowd monitoring is essential for ensuring safety, resource allocation, and informed decision-making. Looking at the majority of existing methods, we observe that they rely on large, computationally expensive models, like the VG16 pre-trained model, which has become a ubiquitous solution in many crowd counting and localization works. However, these are impractical for real-time scenarios, particularly considering the limited hardware found on onboard drones. Our study highlights two major drawbacks in existing works. First, we observe that there is a lack of lightweight alternatives for crowd counting and localization, but also that there is a lack of datasets specifically tailored for aerial data and drone view. To address the aforementioned challenges, the contributions of this work include the introduction of a novel modification to the HRNet, which is now more suited for aerial crowd analysis, that basically removes redundant branches and blocks, resulting in a V-shaped structure, which provides fewer layers, as well as reduction in number of GMAC operations, as well as reduction in number of parameters. We also address the problem of this network having low resolution outputs by utilizing a more efficient sub-pixel convolutional network to operate on a much higher resolution output, which makes it more suitable for aerial imaging. In addition, we trained the model in a composite loss function for better accuracy and demonstrated a dataset that is tailored for aerial imagery, where we have a high number of images as well as large crowd counts, but is more suitable for aerial image analysis than previous works. This diagram depicts the modified HRNet that is now more suitable for aerial image analysis. Our main observation and main modifications in this architecture stem from the fact that we are in no need of utilizing the low feature maps that are generated in this architecture, which are the bottom feature maps in stage 3 and stage 4. However, these do add context, so we remove some of these blocks in the original architecture and focus more on the processing to be done in the higher resolution feature maps. And on top of that, we modify the upsampling of the original model to be done using an enhanced sub-pixel convolutional network, which utilizes 5 convolutional stages, where we increase the number of channels at this stage and then more progressively improving the output resolution. This type of upsampling removes also potential artifacts, which makes it more suitable in our case where the whole model outputs points in a feature map that shows the density of the crowd in the image. Then this dense image is post-processed to extract the count of the people in the image. The accompanying dataset we introduce is comprised of over 6,500 high-resolution images with detailed annotations captured in a wide range of scenarios, such as university campus, as well as urban areas. It includes both sparse and dense crowds, observed under varying environmental conditions, different lighting conditions, which ensures a robust evaluation for crowd counting and localization models. You can see the top row in the images, the example of images, and on the bottom, the ground truth files with the point annotations. You can also observe that compared to aerial datasets available in the literature, we either have a higher number of annotations or a much bigger maximum count of objects, so making it suitable for high resolution dense crowd prediction. Now moving on to the results. First, we show here some ablation studies of the different architecture modifications. We show the changes we implemented and their impact on the localization and counting performance. We observed that with progressive iterations of the architecture, we reduce the number of parameters in the model. At the same time, we also impact the mean absolute error. In the end, the proposed method manages to provide the best mean absolute error, as well as the highest frames per second when measured on a Jetson Orin embedded device, showing that the proposed modifications have indeed reduced the parameters of the model, have also helped improve the counting accuracy, at the same time improved also the efficiency of the model. You can find more details in the paper for these ablation studies. In terms of comparing with related work, we compare different methods, which you can find in the paper, against 4 different data sets. Overall, we observed that the algorithm, even though it was specifically designed for aerialimagery, performs comparatively well in these types of data sets that contain also ground view images and other types of views. And in particular, on the JHU dataset, which is the largest out of the 4, it performs the best, demonstrating the fact that it is still capable of counting in a variety of scenarios. We also provide qualitative results here to show that beyond the fact that the counting performance is quite close to the ground truth, it also focuses on the right parts of the image to count and give us an estimate. So overall, the model achieves competitive accuracy with significant efficiency gains, as it achieves 6.5 frames per second in a Jetson Orin for 720p images. Our work has practical applications in real-time crowd management, public safety, and drone surveillance applications, where efficiency and accuracy are both of paramount importance. So in the next video, we're going to give some examples of real situations and how the model performs in these test environments. In conclusion, in this paper, we present an improved and more efficient algorithm and neural architecture for real-time crowd counting and localization. We focus on removing the redundant parts from the architecture that are not suitable for aerial imagery, while enhancing the parts for output resolution, which play a key role in improving the overall accuracy of the model. Furthermore, we propose a dataset containing high-resolution aerial imagery of dense and sparse crowd areas that can be used for further research in this domain. Our work has the potential to advance real-time crowd analysis and contribute to the development of more efficient and effective solutions. We are eager to further investigate this architecture, utilizing neural architecture search for automating the design of the architecture, as well as improving the dataset and evaluation settings. Thank you very much for your time, and I'm very happy to welcome any questions you may have, but also connect to you on social media so we can continue with the discussion on this work.